Hi, this is Andrea Hendricks, and I want to talk to you about solving quadratic inequalities. Quadratic inequalities are going to be very related to solving quadratic equations and the methods that we've learned thus far to solve those. I want to first start by reviewing a few things with you about inequalities. Let's review a linear inequality first. If I have 3x minus 2 is less than 7, and I want to solve that, I have to isolate the x, right? So we would add 2 to both sides to get 3x is less than 9. Dividing by 3 gives us x is less than 3. But if you recall, that's many, many, many numbers, right? Infinitely many numbers. I can't list all the values that would solve that inequality. So we graph that. So to solve or graph x is less than 3, I put the 3 on the number line and shade the portion of the number line that corresponds to that, and that is all the values less than 3, which is everything to the left of 3. Now another way to write that is in what we call interval notation. Interval notation is from the smallest number in the set to the largest number in the set. This set goes on like to negative 100, negative 1,000, negative 1 million, continues indefinitely in the negative direction. So we write that as negative infinity to 3, and 3 is really not included, but like 2.9999999 is. We can't denote the largest numbers in the set. It's not 3, but it's really, really close to it. So we use the 3 with the parentheses to indicate that we're really close to it, just not including it. Some review of other intervals, like if I have x is greater than or equal to negative 2. Do you recall that means we shade everything to the right of negative 2? But here we can also include negative 2 because it satisfies the inequality, and we denote that with the bracket. So from the smallest, or that is the leftmost to the rightmost, is from negative 2 to infinity. X is less than or equal to 7. We shade everything less than 7, which is to the left, but we can include 7, so we indicate with a bracket. So that's from negative infinity to 7. X is greater than 6 is to the right of 6. Smallest to largest is from 6 to infinity. X is less than negative 4 is to the left of negative 4, which is negative infinity to negative 4. And also notice that on infinity or negative infinity, we never have a bracket. We always have a parentheses because it's something that we can never reach. The other thing I wanted to review is how do the solutions of a quadratic equation and the graph of the associated parabola relate to one another. And here I've looked at x squared minus x minus 6 is equal to 0. And that's solvable by factoring. If you want to use a quadratic formula, you can. But the factors of 6, whose difference is 1, would be 3 and 2. We know they're different signs, the larger one being negative. So we have the factors of x minus 3 times x plus 2 is equal to 0. Setting each of those factors equal to 0, we have either x minus 3 equals 0 or x plus 2 equals 0. So the solutions are 3 and negative 2. Now what do those have to do with the graph? That is, if I graph the side that's opposite from 0, this y is equal to x squared minus x minus 6, and input that in the calculator, I get this parabola. Now we've only looked at graphing parabolas of a special form. Do you remember that vertex form? But any quadratic equation has a graph that is a parabola. You don't really have to worry about how this comes about, but it has a vertex and so on. The value of A determines if it opens up or down, so those things still are important. But this one has a graph that's opening up, and it goes through on the x-axis negative 2 and 3. So those points, that is those solutions, are really the x-intercepts of the graph. That is where y is equal to 0. Now, we're going to talk about using a graph to solve an inequality, and then I'm going to talk about how to do that. But if I wanted to solve where x squared minus x minus 6 is less than or equal to 0, this is telling me to find what values of x is the expression x squared minus x minus 6 less than or equal to 0. Okay. Well, we know where it's equal to 0. It's equal to 0 at negative 2 and 3, right? Because that's the solutions to that equation that we just talked about, which is here at negative 2 and at 3. Let me draw an imaginary line through there. Well, the thing is, at negative 2 and 3, the output is 0. But for every other value of x, the output will either make that expression positive or negative. And in fact, we can tell from the graph or from the table. Look at the table, negative 2 makes the expression x squared minus x minus 6 equal to 0. At 3, the output is 0. But look at negative 3. If I plug in negative 3 to this, negative 3 squared minus the negative 3 minus 6 is saying that that is equal to 6. But 6 is greater than 0, not less than or equal to 0. Well, look what happens between the negative 2 and the 3 at 1, 0, 1, and 2. All of those values for x result in the y value being negative. In other words, those are values of x that make this inequality true. Then if I extended my table and looked at 4 and 5 and so on, I would find that there would be positive values for 4, 5, and so on. So the graph actually tells me the solutions and where they lie. Because where is y less than or equal to 0? Well, y is less than 0 when the points are plotted below the x-axis, right, in quadrants 3 and 4. Y is equal to 0 on the x-axis. Y is greater than 0 above the x-axis. So the only portion of the graph that's below the x-axis is between the negative 2 and 3. So my solution to the inequality would be the interval from negative 2 to 3, because those are the values of x for which the points on the graph are below the x-axis. Well, let's look at how to do it by hand, and then maybe it will make a little bit more sense to cut the graph up from the bottom, so to speak. And I'm sorry I've already written to be so confusing. If I want to solve for x squared plus 2x is greater than 35, the very first thing I have to do is find the solutions to the equation. That is, where does x squared plus 2x equal 35? And that's where x squared plus 2x minus 35 is equal to 0. Again, we can do factoring, quadratic formula, whichever method you prefer. It factors nicely. The factors of 35 whose difference is 2 would be 7 and 5. We know different signs, larger when positive. So we set x plus 7 equal to 0 to get x is equal to negative 7, or x minus 5 is equal to 0 to get x is equal to 5. So the second thing that we do here is we place the negative 7 and the 5 on the number line. Pretend that shading isn't there just yet. Then what we would have to do is determine where do the solutions lie, because if you remember from the graph that we just saw, in a region around those intercepts, the graph is either all above or all below the x-axis. So it's sufficient to just test one number, because if we know what happens with one number in the region, all the other numbers follow suit. So we're going to test numbers in the region. So in region A, that is everything to the left of negative 7. So we're going to plug in, let's say, negative 8. Where are we plugging it into? We're always going to plug into the original inequality. So in place of my x, I put in negative 8 squared plus 2 times negative 8. And I'm testing. I want to ask myself, is that going to be greater than 35? Well, negative 8 squared is 64. 2 times negative 8 is negative 16. So 64 minus 16, is that greater than 35? Well, 64 minus 16 is 48, which is greater than 35. That is true. So that means since this region A worked for one solution in the region, it works for all of them. So that's why we can shade region A to say that solutions to that inequality lie in this region. What about in region B? So this is our step 3 here. In region B, we're going to plug in 0. Well, 0 squared plus 2 times 0, is that greater than 35? Well, the left side of that is just 0, but 0 is not greater than 35. That is false. So since one number failed to work in that region, all the numbers in that region will fail to work. So we cannot include region B in our solution set. And then in region C, we need something larger than 5. So let's say 6. 6 squared plus 2 times 6, is that greater than 35? Well, 6 squared is 36, plus 12 is 48, which is larger than 35. That is also true. So here again, all the numbers in region C work since one number worked. Now what about the endpoints? So really the shading and all is like step 4 and 5 here. We shade the true regions, and then we have to know what happened at the endpoints. Well, the endpoints were from what? From where it was equal to 35, but we're only allowed to be greater than. So we cannot include those endpoints, so we would just put parentheses there. So the solution to this problem, one way to write it is the graph. The other way to write it is in interval notation. So the solution in interval notation, I have it written down here, is negative infinity, right, I'm starting from the leftmost, to negative 7, union 5 to infinity. Okay? Now, I'm also showing here that this relates to x squared plus 2x minus 35 is greater than 0. So in just a minute we can see how the calculator would assist us in solving this problem. The steps to solve the quadratic inequalities, let me first read those using the boundary number method. You have to solve the associated equation, that is, replace the inequality with an equal sign. Place those numbers on the number line. Test a number from each region formed by the boundary numbers. And you're going to shade the regions that are true. Determine the sign to go in the boundary numbers. That is, do we use a parentheses or bracket? If it's less than or greater than, you're going to use parentheses. Less than or equal to, greater than or equal to, you're going to use brackets. But infinity never gets a bracket. It always has a parentheses. And then you're going to write the solution in interval notation. So looking at this example, 2x squared plus 5x minus 35 is greater. Following that illustration, those steps that we just outlined, the first thing I have to do is set 2x squared plus 5x minus 3 equal to 0. I chose to solve it here by factoring, but again, you could do the quadratic formula. To factor it, since this is different than 1, I could say 2 times 3 is 6. And I need the factors of 6 whose difference is 5, and that would be 1 and 6. And then remember, I expand the 5x to a combination of the 6 and 1. We would need different signs, with the larger one being positive. So I put in a plus 6x minus a 1x in place of the 5x. And then we factor by grouping. Between 2x squared and 6x is a 2x in common, and that leaves an x plus 3. Between a negative x and a negative 3, we have a negative 1 in common, and that leaves an x plus 3. So our factored form is x plus 3 times 2x minus 1 equals 0. I set each of those equal to 0 to get x plus 3 equals 0, so x is negative 3, or 2x minus 1 equals 0. So when we solve that, we get 1/2. And then the next step would be to place the negative 3 and the 1/2 on the number line. Again, pretend you don't see the solution to all of that there. And then step 3 would be to substitute values from each of the regions into the original inequality and determine if that is true or false. So out of region A, we need something less than negative 3. So we select negative 4. We plug in 2 times negative 4 squared plus 5 times negative 4 minus 3, is that going to be greater than 0? Well, negative 4 squared is 16. 2 times 16 is 32. Minus 20 minus 3. 32 minus 20 is 12. Minus 3 is 9. And 9 is greater than 0, so that works. Then we have to plug in a number between negative 3 and 1/2. If 0 lies in the region, that's my favorite number to use. So we're going to plug in 0. 2 times 0 squared, that's 0. Plus 5 times 0 is 0. Minus 3 is negative 3. But negative 3 is not greater than 0, so that one is false. Then we plug in a number larger than 1/2, which is 1. So 2 times 1 squared, let's think about that. 1 squared is 1, times 2 is 2, plus 5 times 1, which is 5, so 2 plus 5 is 7. Minus 3 gives us 4, which is greater than 0, so that is true. So we would go up and shade on the number line the regions that tested true, which is A and C. What about the endpoints? I cannot include them because I'm strictly greater than, so I have to use parentheses. So here's my solution in interval notation. Negative infinity to negative 3, union 1/2 to infinity. Okay. Now on the graphing calculator, if I'm trying to solve 2x squared plus 5x minus 3 is greater than 0, I input into y1 the squared plus 5x minus 3. When I graph it, I find that my x-intercepts are the numbers that we found for solutions, that is, those boundary numbers, negative 3 and 1/2. Now, how can that help me? If I draw lines down through the negative 3 and 1/2, I have my regions A, B, and C, if you will. Well, in region A, what's happening to the graph? It is above the x-axis. In region B, the graph is below the x-axis. And in region C, the graph is above. Well, what does it mean to be greater than 0? This says find the values of x for which that y value is greater than 0. Well, where is y greater than 0? That is above the x-axis. So that would happen in the regions A and C. And what about the endpoints? Strictly greater than means I cannot include those. So I would have from negative infinity to negative 3, union 1/2 to infinity. So just knowing what the graph does, I immediately know which regions to include. Excuse me. Another way is to look at your table, right, by doing second graph. And in the table, if I do second graph, I can go to the values of x that I need to plug in and check, right? We said something left of negative 3. So in our region A, we tested negative 4. Well, we got 9. Is 9 greater than 0? Yes, that's true. Then we had to plug in something between negative 3 and 1/2. So we plugged in, what, 0. But at 0, we got negative 3. Is negative 3 greater than 0? No, that's false. Then we had to plug in something larger than half. We plugged in 1. If we plugged in 1, we got 4. Is 4 greater than 0? That's true. So the table can actually do the testing for you without you having to go through and do it yourself. Here's another example. X squared minus x minus 5 is less than 0. A lot going on, and I'm trying not to get distracted by what I already have written here. The first thing is you solve the equation. X squared minus x minus 5 is equal to 0. Well, unfortunately, this one doesn't factor, so I have to use the quadratic formula, with A being 1, B being negative 1, and C being negative 5. So when we plug into negative b plus or minus the square root of b squared minus 4ac all over 2a, I would have x is equal to the opposite of negative 1 plus or minus the square root of b again, which is negative 1 squared, minus 4 times a, which is 1, times c is negative 5. And that's all over 2 times a, or 2 times 1. Well, inside parentheses, or the radical rather, negative 1 squared is 1. Negative 4 times 1 times negative 5 is plus 20. So 1 plus 20 gives me 21. So I have as my solutions either 1 plus the square root of 21 over 2 or 1 minus the square root of 21 over 2. So I would put those on the number line, knowing that the 1 plus the square root of 21 over 2 is larger. In fact, if you use your calculator to approximate that value, it is 2.8, or approximately. 1 minus the square root of 21 over 2 approximated as a negative 1.8. Okay, so those are the approximations that will allow me to know which side I need to put the numbers on. So then I have to test a number from region A, B, and C. So out of region A, I need to choose something smaller than negative 1.8. So let's say negative 2. So I'm plugging back into the original inequality here. Right, negative 2 squared is 4. Minus a negative 2 would be plus 2. Minus 5 is 6 minus 5, which is 1, which is not less than 0, so that's false. In region B, something between negative 1.8 and 2.8 is 0. So 0 squared minus 0 is 0. Minus 5 is negative 5, which is less than 0. That is true. So I shade region B. In region C, something larger than 2.8. So I've chosen 3, but you could use 4 or 5, doesn't matter. 3 squared is 9. 9 minus 3 is 6. 6 minus 5 is 1, which is not less than 0, so that's false. So the only region that tested true is region B. Now, what about the endpoints? It's strictly less than, not where I can include those, so I have to put parentheses. So in interval notation, here's my interval. I have parentheses at 1 minus the square root of 21 over 2 to 1 plus the square root of 21 over 2. Okay, so that means all the numbers between those two endpoints. On the graphing calculator, if I look at x squared minus x minus 5 is less than 0, and if I input to y, x squared minus x minus 5, and graph it, my solutions are the negative 1.8 and that positive 2.8, which is really 1 plus the square root of 21 over 2, 1 minus the square root of 21 over 2. And then I look at what happens around those endpoints. Right, here's my region A, B, and C. If you can solve the equation and get the endpoints and then use a calculator, you have pretty much everything else that you're going to need for this. What's happening in region A? The graph is above the x-axis. In region B, the graph is below the x-axis. In region C, the graph is above. Well, I wanted where y was less than 0 or where it is below the x-axis, and that only happens in region B, and the endpoints are not included. Here again, I can look at what did I test. In region A, I tested negative 2. In region B, I tested 0. And in region C, I tested 3. So you're looking, is 1 less than 0? No. Is negative 5 less than 0? Yes. Is 1 less than 0? No. Okay. Now, some last examples is x minus 3 squared. So the first thing we do is set x minus 3 squared is equal to negative 4. We can use the square root property to solve that, to get that x minus 3 is equal to plus or minus the square root of negative 4. But recall here, the square root of negative 4 is 2i. So I really have solutions x is equal to 3 plus or minus 2i. But the problem is, those are not real numbers. So when I draw my number line and place numbers on my number line, there are no numbers to place. Okay? So I only have one region to test, region A. And pick any number off the number line you like. So I'm going to plug in 0. If you plug in 0, 0 minus 3 squared is 9, right? Because 0 minus 3 is negative 3, but negative 3 squared is positive 9. 9 is greater than or equal to negative 4. That's true. So that means if the one number from that one region tests true, every number is a solution to that inequality. So my solution in interval notation would be from negative infinity to infinity, or all real numbers. Maybe you can make sense of that from the original problem. When you square anything, what are you going to get? Yeah, something that's positive. And a positive number is always greater than or equal to a negative number, right? That's always true. So no matter what value you use for x, you're going to get a true statement there, which is why we get all solutions. Now, if I just do a simple thing as reverse that symbol to make that less than negative 4, the boundary numbers don't change, right? Because I still replace inequality with an equal sign. So I still find that I have no numbers on my number line when I partition it by the solutions. We test one number from that one region, so 0. But when I plug in 0, 0 minus 3 squared is still 9. Is 9 less than negative 4? That's false. So since that one region doesn't test true, we can't shade anything on the number line. So our solution in this case is the empty set. There's no solution. Well, here again, I'm saying a positive number is less than a negative number. That's never true, right? So I'm going to have the empty set for that one. Now on the graphing calculator, well, we were trying to find where x minus 3 squared is greater than 4, or I can think of that as where x minus 3 squared plus 4 is greater than or equal to 0. So if we plug into y, x minus 3 squared plus 4, and graph, well, greater than or equal to 0 is saying where is that graph above the x-axis? Well, the graph is above the x-axis everywhere. So that would tell us that the whole number line is a solution. If I'm trying to find where x minus 3 squared plus 4 is less than 0, right? That's saying where is the graph below the x-axis? Well, nowhere is it below the x-axis. So that is the empty set. So since it was all above, or everywhere above, my solution is all real numbers, or negative infinity to infinity. But likewise, that makes the less than 0 no solution because it's nowhere below. Okay. You can also use the table. Right, every value that you plug in for x, you're going to get something that's larger than 0, never less than 0. So that would tell you there's no solution to this second part. Okay. So call me if you have any problems. Thanks.